In this video, I want to take a look at transformations of lines and the unit square. Here's the theorem. If T from R2 to R2 is multiplication by an invertible matrix, so we're multiplying by an invertible matrix, so this is a matrix transformation, then 5 things. The image of a straight line is a straight line. The image of a line through the origin is a line through the origin. The image of parallel lines are parallel lines. The image of the line segments joining P and Q is the line segments joining the images of P and Q. And the images of 3 points lie on the same line if and only if the points themselves lie on the same line. Okay. Now, I'm not going to prove this, but I'm going to give you an example, and perhaps you can see where the proofs would come from. The first one, the image of a straight line is a straight line. Now, the textbook actually uses, they give an example, but they do it in terms of an equation like 3x plus 2y equals 5, right? And so they have an equation of a line, and then they do the transformation on xy and show that the result satisfies the equation of some other straight line. Okay. Now, the way I want to do it is I want to look at the line parametrically, right? Since we're multiplying by a matrix, it makes sense to me to represent the line in a vector form. So look at the point xy equals 4 plus 3t, 2 minus t. This is a line that passes through the point 4, 2 and has slope, negative 1 over 3, so negative 1/3. Parametric representation. But this makes it easy for me to just multiply this point times the matrix. Right, so I'm just making up a matrix here. 1, 2, 3, 4 is my matrix that I'm going to use. And so if I multiply by the point xy, it's multiplying by this. And so essentially for each value of t, I'm calculating by this calculation where the image is. So I get the whole line transformed in that statement, or in this calculation. So anyway, just multiplying it here, I've got 1 times 4 plus 3t, plus 2 times 2 minus t, and then 3 plus 4 plus 3t, and then plus 4 times 2 minus t. Gather some multiply that out, gather some like terms, and I get something that looks like this. The result of this transformation is the x-coordinate is 8 plus t, and the y-coordinate is 20 plus 5t. Well, I can see that this is a line that goes through the point 820 and has slope, 5 over 1. And perhaps you can see that for the way you parameterize a line, it's like you've got the x-coordinate of the point you want to go through plus the x-component of the direction vector, and then the y-component of the point you want to go through, and the y-component of the projection vector here. Not projection vector, of the direction vector of the line. And so this is going to be linear, that's going to be linear. You do this multiplication, it'll look just like this. The constants will combine and the t's will combine, and you'll end up with some linear relationship here. That the first component is linear, the second component is linear. You've got the description of a line. Okay. Now, the invertibility of this is important, right? The image of a straight line is a line. I showed that here, that the image of this line is a line. But if this was not invertible, say, for instance, if you're projecting down onto the xy plane, onto the x-axis, you could have a vertical line that all gets projected down to a point. So your image of your line would not be a line anymore, it would just be a single point. But if it's invertible, if it's an invertible matrix, then it turns out that you're not going to do something like that. That is, that vertical line is going to be sent through some other line somewhere, whatever the transformation is doing. Even the y-axis, when you project down to the x-axis, the whole y-axis ends up at the origin. So that's not a line anymore, that's just a point. Now, we could say that even if it's not invertible, you're going to get a line or you're going to get a point. That would be true. Anyway, how about the image of a line through the origin is a line through the origin? Well, we've already established that that the image of a line is a line. It's just a matter of does it go through the origin. Well, we know that under any matrix transformation, the origin goes to the origin. So if the original line contained the origin, then that point at the origin is going to be sent to the origin, right? So it'll still be a line through the origin. The image of parallel lines are parallel lines. In vector form here, the difference between the difference in the parametric equations for two parallel lines is simply a matter of what point does it go through, right? You're going to have the same direction vector. You're going to have the same slope here. So 3 and minus 1, if you had another line parallel to this, it would have a 3t and a minus t as well, but just have different numbers over here, 4 and 2. And so when you do this multiplication, you can see that what happens here, the 1 is still going to be multiplied by the 3, and the 2 is going to still be multiplied by the minus 1, and likewise down here. Yeah, these numbers are going to be different, but the stuff in front of the t's are going to be the same. So the result that you get will still be have a 1 and a 5t. Now, these numbers will be different, so you'll end up with a different line, but it'll still be parallel to this one, right? Because these coefficients in front of the t's will end up being the same. The image of a line segment joining the points P and Q is a line segment of the image, yes. So you start with 2 points and the line segment between them. They get transformed somewhere, and you get the line segment between them. That's just a matter of, what values of t are you plugging in? And you can show that the t's that get you from here to here are the same t's that get you from the image, or let's go this way, from this image to that image, right? It'll get you that same piece. Essentially, this is saying that even though we know that the line is going to the line, it's not taking, the transformation is not taking the line and somehow flipping it around and putting it together in a different way. It's like if it was connected this way before, it's connected this way afterwards, right? Things don't get switched up. They just stay in the same order. Right? And likewise here, the image of 3 points on a line, the image of 3 points lie on a line if and only if the points themselves lie on a line. This is saying that these transformations, they're not going to take 3 points that are not on a line and end up putting them on a line, or they're not going to take 3 points that are on a line and take them and put them not on a line, right? That these 3 points, 1, 2, 3, if they're not on a line, you transform them, they're still not on a line. If they are on a line, you transform them, they're still on a line. Okay. That just matrix transformations keep straight things straight. That's what they do. And again, this was just in R2. There's a similar theorem up in R3, which would say lines go to lines, but also planes go to planes. If the matrix is invertible, if this is a 3 by 3 matrix, then it would take a plane to a plane, and a plane through the origin to the plane through the origin. And you could go on up in the dimensions, and that essentially the theorem is straight things stay straight without mixing them around. So here's a picture of what we just had. The original line that I first had was the line that goes through 4, 2 with slope negative 1/3, and it got transformed into this thing. It goes through 820, which is up here somewhere, up there, and slope 5. Actually, I can see it as slope 5 because it goes through those 2 points there. Anyway, a straight line got mapped to a straight line. Now, a way to visualize transformations is to look at what happens to the unit square. And by the unit square, I mean a square that's got one corner at the origin, one corner at 1, 0, one corner at 0, 1, and the other corner out here at 1, 1. And you say, what does the transformation do to that square? And it gives you an idea of how the plane is being moved around, right? So for instance, reflection about the y-axis. This square gets flopped over to that one. Now, I don't think this picture is adequate to really show what's going on, because did that square get moved over? Did it get rotated over? Did it get flipped over? Right? That there's different ways that you could take this square and move it over to there. Right? Now, granted, they are paying attention here to where does the point 1, 1 go to, and in this case it goes to minus 1, 1, that corner there. The origin always stays at the origin. But it's not clear to me whether this square It's like, yeah, I can take that square and flop it over like this, or I could also flop it over. I could flop it and flip it essentially. There's two different ways that I could get this to there, having both this corner and that. Having those two corners end up in the same place. It's just a matter of where are these two corners. Likewise, this reflection. Right? So I would really like to look at this in terms of the following. Let's see if I can pull this up here. Yeah. So that reflection that we just had was flopping over the y-axis was this, if I can make that negative. Okay. So the green moves over to the red. Right? And I have this set so that I can animate it. And you can see that it gets flipped over to that side. The thing is, I could have rotated it over there, and it would look different. Let's see if I can rotate. Say, all right, there we go. So this actually is taking the unit square and moving it over there to the other side. But this time, the green flag ends up above. With the reflection, the green flag ended up down below. Okay. So there's a little bit more that you can see by shading half of the square and looking at how that moves. I think of it as like a flag. How does the flag get flipped around there? Right? And we can see a lot of stuff about these images. So, for instance, that was the rotation. If I just had a +1 here, this is reflection across the line. So this is matrix B. This is reflection across the line y equals x. So now this just gets flipped over, and the unit square ends up on top of itself, but it ends up on top of itself upside down, right? The whole plane gets flipped along the line y equals x. How about one like this? How about matrix C? Let's go with C here. C is an expansion by a factor of 2 in the x direction here, right? And so when I look at that, the unit square is being pulled out to twice as big in the x direction. I want to point out, if that was a -2, then this is being expanded and flipped, right? So it's an expansion by factor 2, but it's also being flipped over the y-axis. So I think of it as expansion by -2, but think of it as a flip and an expansion, if you will. D here is a shear where the unit square is being sheared over to sheared in the x direction. Right? So the output, the x coordinate of the output is the old x coordinate plus 2 times the y coordinate, right? So the x coordinate is being moved over more than it would be otherwise. Right?